Okay, good morning. What I was going to do for this short 15-minute talk is to go over sort of the candidate GMPs that we're considering. And this is sort of the list of ground motion model prediction equations that we're using that will be presented for the sensitivity analysis in future talks this morning and also later today. So just going back and looking at the list, there's 14 models that we're currently considering and we're using in the sensitivity analysis. And they're listed here on the chart, on the slide. The first 5 are actually companions in the sense that first you have the NGA West versions of the models, so the vintage 2008. And then also listed on each line you have the current models, the NGA West 2 models. And so from the first workshop to now, there's been modifications and refinements on these NGA West 2 models. But you can see they're the same 5 developer teams. And so those 2 sets of models are sort of paired together. You've got the NGA 2008, and then you've got the current NGA West 2 models. The other models, the other 4 models that we've considered so far are the Gregor and Kalkin model, 2013, which is a model which we also looked at in the first workshop. The Zhao et al. Model, which is from 2006. His model was for not only crustal events, but for subduction, slab, and interface events. But of course, we're only looking at the crustal version of his model. And then there's a new model from the European data set that's come out by Akkar et al., the 2013 version. And then finally, as Norman mentioned, the Bindi model, 2011. And that is basically the Italian data set and contains a lot of normal faulting earthquakes. I'll go through just briefly sort of the databases that go into these individual models. So what I'm showing here is a companion comparison between the NGA West 1, the 2008 model or database, and the current NGA West 2 model. Going from the NGA West 1 database to the NGA West 2 database, you're going from about 3,500 records up to over 20,000 records. So it's a huge increase in the data set. And as Norm just mentioned, you can see on this figure here of the magnitude distance range, these orange plots, which are down here below magnitude 5, are those small magnitude events. So it's greatly increased that data set. And also in comparison, you can see the red dots are now the new events from the NGA West 2 compared to the blue dots being from the NGA West 1. There's some significant events which have been added from China, Japan, Italy, New Zealand, Taiwan, and as well California, Mexico. And if you look at a geographical distribution, you can see the blue symbols here on this plotter from the NGA West 1 database, and then the red ones are from the new NGA West 2. So you can see again there's the events in China, Japan, down here in New Zealand, and as well the Italian data set. So this is a huge increase in the database for going from NGA West 1 to NGA West 2. And it represents the largest database for all of the GMPs that we're considering and we're looking at. If we look at the Gregor and Kalkin model, the 2013 version, theirs was primarily based on the NGA West 1 database. So what I'm showing here, this is a figure from the 2008 Spectra paper. This is actually showing the distribution of just the NGA West 1 database. But they've also added some more recent events. So specifically the Parkfield event, magnitude 6 in 2004, and the 2003 San Simeon event, the magnitude 6.5 event on the central coast of California. They've also added some various events between magnitude 5 to 5.7 from Turkey and also from Armenia. So this plot of their magnitude distribution is just the NGA West 1 database, and so you'd need to add to that the events occurring from these other two events here, and then as well the other events from Turkey and Armenia. If we look at the Zhao database, as I mentioned, his development of his model included both crustal events and subduction events from Japan. And so in looking at this figure, which comes out of his paper, the blue symbols here are the crustal events, and the red and the black symbols are the 2 different types of subduction events, so being the inner slab and the interface events. So again, he developed a different model for each type of seismic source, and we're only looking at the crustal model. So you can see his distances range from about a little bit less than a kilometer, but primarily up in the 10 to sort of 100 kilometer distance range. His magnitude is cut off at a magnitude of 5 and goes up in the crustal sense to about just under 7. That's just for the Japanese events. Then he also added some significant events from Western US data sets for distances less than 40, because for his crustal model he said he wanted to increase sort of the large magnitude, fairly close in distance range. And as well, he added the records from the 1978 Tabas earthquake. The other thing he looked at is he broke his events down by focal depth because he wanted to make sure that he wasn't classifying any crustal events with a very deep hypocenter because he has a depth term in his relationship. And so you can see here all of his crustal events are plotting with the depth of less than about 25 or 30 kilometers in depth. If we then move to the Ackar et al. Relationship, this is again a European database. It has about 1,000 records or so that were used ultimately in the model. And I should mention in the Zhao relationship for the crustal, he had about 1,500 records that went into that development of his model. What they did is they looked at the European databases that had been developed over time, and then they went through and sort of refined it. They only selected those records which had a measurable VS30 value for the stations, so that eliminated some of the stations that had sort of inferred VS30 values. And in this plot, what they're showing again is a magnitude distance distribution where they're showing distance across the bottom and magnitude going up from 4 to 8. They've broken it up into sort of shear wave velocity bins. So you've got greater than 800 meters per second up here on the top left. You've got 360 to 800, 180 to 360, and then less than 180. So they have some that are less than 180. The other refinement that they're showing in this plot is they've broken it up by fault mechanism. So you've got normal, reverse, and strike slip. And you can see that there's actually fairly decent amount of normal events from this data set because it's European events and a lot of the Italian events are normal faulting events. If we then look at the Bindi relationship, and I think that should be 2011, not 2013, I apologize for that. What they did is they looked at the events that are occurring in Italy. And so you can see here's a geographical representation. They initially collected all the data sets and then they went back and they refined it. And so they wanted to remove any stations that only had a single recording from one event. And then they also wanted to remove events where they didn't have a good estimate of the moment magnitude. And so initially, this is their distribution, their bins of magnitude and number of records. You can see that between 4 and 4.5, they've got over 400 records. But the purple and the green are the records that they removed. So when you get down to it, what they actually used are the gray boxes here. It's about 700 to 800 records. About 75 to 80% of these events are normal events. So this is why this is one of the GMPs that we're considering because it has a lot of normal events. We did look into how many of these significant normal events are contained in the new NGA West 2 database, and those are actually in the pure NGA West 2 database. So we don't feel that we've missed any of the significant events from the normal faulting events in Italy that are contained in the Bindi data set. Just sort of summarizing, one of the things that we'll be showing later, I'll be talking about tomorrow, is sort of how do these models behave as you go out for different magnitude and distance ranges. Because as we know for the Arizona plant, we're considering sources that contribute from large events in California on the order of 200 kilometers or so. So if I just made a quick summary table, these are the recommended applicability ranges in magnitude and distance for the GMPEs. And for the most part, they are applicable up to the large magnitude, up to about 8, 8.5 in most cases. The one that is not is the Bindi, and although they didn't specifically state their range of applicability, you'll see a little bit later that the largest event in their database is a 6.9, and when you extrapolate it to larger magnitudes, some interesting and probably non-preferable things happen to their model. In terms of distance, they're all sort of applicable to the 200 to 300 kilometer distance range. So for the most part, if we're looking at sources out to about 200 kilometers, we're not really extending these models quite a bit further than their recommended application. The other thing I just wanted to summarize for these models is sort of the site classification. So for the NGA West 1 models, which are listed here on the top 5, 4 out of the 5 were defined in terms of a VS30 value. The IDRIS model was actually binned into 2 site categories, so 450 meters to 900 meters per second and greater than 900 meters per second. So that was actually a bin value type of model. Down below here on the bottom, you have the 5 NGA West 2 models. The only difference now is the IDRIS model now has a sort of functional form for the VS30, so it's no longer a bin classification for the site response. Then if we look at the other 4 non-NGA models, you can see that 2 of them are actually still bin values. So the Zhao model is defined on certain categories, rock categories, and for all the presentations I'm doing, I'm using his site category 1, which is for shear wave velocities of greater than 800 meters per second. And then as well, the Bindi classified their things in terms to be consistent with the Eurocode relationships. Given all that, in sort of this summary overview, I've got 4 sort of sets of plots of scenario events. And so these are sort of general scenario events. They're not meant to represent the controlling magnitude or earthquakes at each of the 2 plant sites, but just sort of get a good understanding or a good feel for how these models are behaving. So the first case is magnitude 7 for a vertical strike slip fault, dip of 90 at a rupture distance of 10 kilometers. So we're 10 kilometers away from magnitude 7. There are some additional terms, input parameter terms that are needed for the GMPEs, and I've listed some of them here. For example, the top of the rupture, based on a recommended default for magnitude 7, it's just about 1/10 of a kilometer down beneath the surface. The hypocentral depth is at 10.4 because the Campbell-Bezonia NGA West 2 model now needs a hypocentral depth. And all these comparisons are for VS30 of 760, although for the cases where there are bin values, obviously it wouldn't be any change if you went from 760 to 750 or something like that. What I'm showing in the top frame are the median spectra on a log-log plot as a function of frequency. And then on the bottom frame, you've got the same thing, but it's a log linear plot. So you can see the distribution a little bit easier than you can on the log-log. It's about a factor of 1.5 or 2 for this case as you go across in the spectral frequency range. The models are indicated here in the legend. I'm not sure how well they can be seen from the back. The NGA West 2 models are shown as the first 5 here in color, and their companion NGA West 1 versions down here are shown in black and white, but with the same line types. So if you're able to see that, you can compare, for example, the red solid curve is the Abrahamson, Silva, and Kanai model for NGA West 2. And that compares with the solid black line, which is down here, which is the Abrahamson and Silva 08 version of the model. If we look at another general scenario now, we've moved out in magnitude and distance, or moved up in magnitude and distance. So now this is looking at a magnitude 8 from, again, a vertical strike slip fault. We've now moved it out to 200 kilometers. And so the depth to the top of rupture is now at the surface based on magnitude 8. The hypocentral depth is a little bit shallower. It's basically the same, and it's again 760 meters per second. One model obviously stands out in the high frequency range. This dashed line up here is the Bindi model, and this is, as I mentioned before, their largest event in their database was a 6.9, and their high frequency extrapolation for large magnitudes is not just a large distance, but it's also a large magnitude isn't well constrained, and you can see you get a spectral shape which is quite funny looking. It's basically flat to 10 hertz, and then it dips down and remains fairly flat from about 7 or 8 hertz all the way out to about 0.3 or 0.5 hertz. The other things to notice with this plot compared to the previous plot is now we get a huge range in the models. This is now about a factor of 10 if you look at 1 hertz here in the distribution of the model. It's not quite as severe down here at the PGA, but this is a huge range in the ground motion models. If we now move to the third case, this is a magnitude 6.5 reverse fault, and now we're sitting on top of the hanging wall, and so we're at a rupture distance of 5 kilometers. So we're sitting right over this magnitude 6.5 fault, and we've got the top of the rupture coming near the surface with a hypocentral depth of about 9 kilometers. And the things to see in this is now, if you remember back from the first case that I showed, we've got a larger distribution now here, not as large as the magnitude 8 at 200 kilometers, but we still get a range of a little bit over 2 here in the ground motion models, and it's fairly uniform throughout all of the frequency range. I'll go into more detail tomorrow in the presentation of specific comparisons of things like hanging wall versus footwall for the individual models to sort of illustrate certain features of the different models. But this is just sort of a general overview and a summary of the GMPEs that we're considering in the sensitivity analysis. Then finally, the last one that I'm going to do is, this is more sort of applicable to the Arizona site. This is a magnitude 6.5, but now on a normal fault with a dip of 60 degrees, and now we're sitting on the footwall side. So we're at a distance of about 15 kilometers. Again, you've got the VS30 of 760. The thing to sort of look at this and see is that the distribution of the ground motion models, the 14 models, is a lot tighter here than it was for the hanging wall. So even though you're basically the same magnitude, you've now gone from a reverse fault on the hanging wall to a footwall side a little bit further away on a normal faulting event. You've got less epistemic distribution here of the ground motion models. Then finally, the last thing I want to show in this sort of general overview is, of course, when we run the hazard, it's not just the median ground motion models, but it's also how does the sigma impact things and how does it match with the models. There'll be a lot of sensitivity plots that I will show for Diablo and Melanie will show for the Arizona site, emphasizing these aspects in a tornado diagram. But you can see here, this is a distribution of the total sigmas for two different cases. So for the magnitude 7 at 5 kilometers and magnitude 6.5 normal fault at 15 kilometers, you can see there's quite a range here in the sigma values, the total sigma values. If you remember back, the bending model having issues at the large magnitude, large distance, of having high frequency values that are quite high, you'll see in some of the plots a little bit later that for some of the median values, the bending model is low, but their sigma value is the highest of any of the values. So by the time you throw it into the hazard sensitivity analysis, they trade off, and in some cases, they end up plotting in the middle with the other models, and then when you break it out into contributions from the sigma and the media, you can clearly see why they're separating. So you can see here that the two highest sigma models are coming from the Akar et al. And the Bindi, so the two European data sets, and then the NGA models are sort of a little bit lower and sort of cluster down in this range. And so these are sort of the overview of the candidate models that we're considering and that we'll be talking about going forward in both the hazard sensitivity analysis that I'll present and Melanie will present, and as well tomorrow when we start getting into the specific features of each of the individual models and talk about their use and their development that went into those features. And then this is finally just my list of references for the models.